In all of the stuff we did previously this week and the last week in chapter 9, we were testing against a benchmark, a known value. We had some expected mean or proportion that we were trying to see, hey, is our sample in line or out of line with that? But it is quite frequent that what we instead want to do is work with two different samples and compare them against each other before or after a particular treatment. There's a really standard one done for memory. A question for you. Does caffeine affect memory? So what we would do is we give people a list of 30 words to memorize. You've got 5 minutes. Here's the list. Then we wait 5 minutes. And then you have to write down as many of the words as you remember. Another group, you get that same 5 minutes with a different list and a caffeinated beverage. The amount of caffeine somehow indexed against your weight. So it works out to be, grams per kilogram of body weight or something like that. And then at the end of the 5 minutes of looking at the list with your caffeinated beverage, you get another 5 minutes. Then we ask you to recite as many words as you can from the list. Sometimes you have 30 minutes in between. Sometimes depends on the test. But then I want to know, is the average number of words without caffeine different than the average number of words with caffeine? So I have an experiment and a control group. Or I'm looking at, even within one population, I can take different samples, and the sample variation might come into play there. So it is often the case that I will do multiple samples and then see if I can get an aggregate behavior. On page 366 are several examples, but the one I remember most distinctly is the recent change in diet sodas. Anybody drink diet sodas in this room? What do you drink? Why that one and not Diet Coke? What the hell was the change? Seriously, that's a question I don't know. What's the difference between Coke Zero and Diet Coke?
I think Coke Zero doesn't have caffeine. Diet Coke still has caffeine.
On the contrary, Coke Zero is very thoroughly caffeinated. But they changed the formula for the sweetener. So one of them is sweetened one way and one the other way. And by tweaking that formula just a little, then they figured out, well, I can now market to more groups and I can pull in more people. You said it tastes better. How'd they do the survey? How'd they find out? Back in the 80s, Pepsi and Coke were having this huge battle over which one tasted better. The thing that eventually ended up lighting Michael Jackson's hair on fire. Pepsi commercial he did at the Super Bowl. That was the middle of the Cola Wars, and they were really trying to figure out which one tasted better. So Pepsi went into the middle of a busy street with 2 empty cups of brown soda. Said, we're going to pour a different thing into each one, and the bottles are unmarked. Which one do you like better? They want the proportions, right? How accurate? What's the difference between those two proportions? People that prefer A over B. So if I'm trying to do this, and it's still the same process, I need a null hypothesis, I need an alternate hypothesis, I need a decision rule, test, and a table. So I can find out. So, depending on what I know and what I'm trying to test, we're going to be in the same boat we were last chapter. Do I use the Z table? Do I use the T table? How do I know what's going on? Let's start with means. So I have mean 1 and mean 2. And I don't know if they're the same or if they're different or what's supposed to be going on. But I can now say, maybe I think they're exactly the same. Maybe I think they're only apart by 1 or 2. But let's suppose that there is some possible difference, D0. 99.9% of the time, that's the number 0. I think the average should be the same, regardless of which group you're in. I don't think caffeine has any effect on short-term memory. So I think the number of words you can recite with caffeine is the same as the number of words you can recite without caffeine. Well, then I can actually ask for a hypothesis. Either the difference is D0 or it isn't. So I look at the difference between the means. Now, I'm going to be able to do the same 3 different kinds of tests we did last time. So I'll have a left tail, a 2 tail, and a right tail. If I'm doing a left tail test, then my alternate hypothesis is to the left. If I'm doing equals versus not equal, that's a 2 tail test. Because it could be bigger or it could be smaller, I don't care which. And the right tail test means that my alternate hypothesis says, oh, we're bigger. So just like we did before, each problem setting is going to ask me, do you think these means are equal, or do you think they've got a particular difference? Do you think that one is particularly bigger than the other or particularly smaller than the other? Okay. I need a hypothesis setting, and then I need a test statistic. I need to go out and do my samples. So I get from group number 1, I get an average from them. From group number 2, I get an average from them. And then I need a test statistic. Now, since I've done sampling, I have a sample average for each group. How did we do this with one average? We did a test statistic for one average. What did we calculate? It was either Z-calc or T-calc, depending on which way we did it. But what was that formula? This is why you guys get a formula sheet that you should already be preparing. Exams in 2 weeks, people. Aha! I took the average, subtracted the one I expected, the expected value, mu sub 0, and then divided by the standard error. And whether I knew the standard error for the population, or if I only knew it for the standard, for the sample, is what told me whether I was doing Z or T. So when I go to do this test statistic, I need to know whether I'm computing a Z or a T. And the difference was whether or not I knew the standard deviations for the population. And if I get to use the Z values, then I get to use the table that has the Z values, and that's my normal distribution. I don't have a formula for this Z thing yet, because it can't quite be the same as the other one, because I've got two means to deal with at the moment. So I have to kind of figure out what the new version should be. There'll be two sigmas, won't there? Or if I did different samples from the same population, I still need to know something about the standard deviations involved for the whole populations. What if I don't know those? Well, then I can compute my standard deviations, S. And I can use the sample standard deviation. Then I'm using the t-tables and the t-distributions instead. Now, there is also the option that because I have two different standard deviations, that we may or may not be able to group them together. The formulas for the following pieces suck. So in your textbooks, if you've got the electronic version up, if you've got the paper version in front of you, turn to page 368, 369. There are three big yellow boxes on these pages. These formulas absolutely suck. This is why I don't want you to have these things memorized, and we will try and find as many ways to do these in computations like Excel as possible, so I don't have to do them by hand. But option number one, I know the population standard deviations. Two populations, two standard deviations, sigma 1 and sigma 2. Okay, the old version was to take the average and compare it to the expected average. Well, now I'm taking the difference and comparing it with the expected difference. And then I'm dividing by the standard error. But wait, there are two. So instead of using two separate standard errors, I have one combined standard error. Wait just a minute. Sigma 1 comes from sample 1. X bar 1 comes from sample 1. So N1 is? What's N usually? Sample size. So it would be how many samples I took in the first group. Similarly, X2 bar and sigma 2 come from the second group. So N2 is the number of samples taken in the second group. Now this assumes, as we will for all of this chapter, that these are independent random samples. And we have enough of them so that we can assume in general that we have a normally distributed population, even if we don't know the standard deviation for it. And I'm assuming that we either have a normally distributed population or that I have a big enough sample size that I use the central limit theorem and say it's close enough to normal. I don't need to worry about T versus Z. Now remember, that 30 is an arbitrary line. Some books use 35, some books use 100. I don't know. This book says 30. But once I've calculated that number, I'm going to do exactly the same thing we did last time. I'm going to find a critical Z value, whether that's for one tail, that's Z alpha, or for two tails, it's Z alpha over 2. And then I'm going to ask, is our Z out? Or is it in the good area? If it's out, reject. If it's in, don't reject. And that depends on which hypothesis we're using, right? If we're using the left tail, then if my calculated one is too small, we reject. If you're using the right tail, if my calculated one is too big, then you reject. If I'm using the two tail, it can go either way. We use absolute value there. Advantage. You've done this part before. On the other hand, Nick, with what you were asking me on Wednesday with the p-value idea, I haven't talked about p-value, but the same thing will apply here. I could compute the p-value for this and compare that with alpha. This is a very theoretical discussion, but notice that this is the version that requires us to know the most about the situation, because we have to know the population deviations. And that's not always easy to know. So if I don't know the population deviations, then I have to compute S1 and S2 instead. And this is more common. Don't use a slash, comma. And I have to use S1, S2. Sorry, I don't know sigma, I have to use sigma. That's a stupid thing for me to write down. Okay. In this case, I actually end up with another question to ask. I know that I'm taking samples. And when I take samples, I get sample variation. Some samples are a little bit to the left. Some samples are a little bit to the right. Some samples are very wide. Some samples are very narrow. So my sample deviations may or may not be equally skewed over the region. So here's my next question. Okay. Now you may be asking me, why the hell would I ask this question? It is possible that I am taking two different samples from the same group, right? From a group of college students, all undergraduate students at Seton Hill. I'm going to pick 15 people who did this thing and 15 who didn't and see what the results were. Did you go to welcome weekend events? Yes or no? I can find out then from there, how is your campus involvement? Does it affect campus involvement? But then you are coming from the same population, undergraduate students at Seton Hill. So I should assume that the population from which I got sample 1 has the same standard deviation as the population I got sample 2. If I do that, then what I can create is called a paired or pooled variance. And I will call that sigma p. for pooled, oh no, sorry, not sigma, SP. And then I don't have to use two different standard deviations. I use the same standard deviation twice. Yes, ma'am. Pooled. No, I'd rather you ask me than just sit here and stare at me going, what the did you write? I'm writing quickly to try and get my words on paper caught up with my words coming out of my mouth, and my handwriting already sucks, which is why I write with these crazy pens, because they slow me down. Imagine if I was using a pencil, my handwriting would be even worse. Okay, notice what I said here. I'm using this SP, this pooled variance, to find T calc. Why T? Why not Z? Don't know the population standard deviations. I'm using the ones from my sample, therefore I have to use a T value. Wait a minute, what do I need to do a T value? When I go to look at the T table in the back, I need something before I find cutoff values, right? What do I need? Say it again. Degrees of freedom. Now, what are the degrees of freedom normally? But I have two different ends this time, right? So I'm actually going to subtract 2, one from each of them. Now, here's where the ugly stuff starts to happen. I need to figure out how to make SP, that pooled variance. And it turns out SP squared is N1 minus 1 times S1 squared, and 2 minus 1, S2 squared, over N1 plus N2 minus 2. We're basically creating a weighted average. I did weighted averages. That was way back in chapter 4 where we did descriptive statistics. And lo and behold, it comes back. The variance from group 1 is S1 squared. The variance from group 2 is S2 squared. How many times did that occur? How many times did this one occur? And then divide by my total. Instead of using sigma 1 and sigma 2 like I did in the T calculation, in the Z calculation, I will use the pooled variance in the T calculation. Wait a minute. That formula that I just wrote down, here's the Z calculation right here. Notice the only thing that's different is the standard deviations. So that's version number 2. Version 1 was for Z. I knew the population standard deviation. Version 2, I don't know the population standard deviation. but I can assume that the population standard deviation is the same. Huh? That means there's a version 3 where I can't make that assumption. If that's the case, no pooling. That means I need to use S1 and S2 in the right places. Wait a minute. That's going to make my T formula nice and easy. So the only difference between the formula at the top and the formula at the bottom is whether or not I am using pool variance or the separate variances. When I do that, that gives me a little more conservative estimate for the t-value. It makes that a little bit smaller. Wrong question? Okay. We're looking going, wait a minute. What happens in this problem is that the degrees of freedom change. Two guys, Behrens and Fisher, noticed that this was a problem. And one of their students, a guy by the name of Welch, came up with an adjustment. And he said, hey, if you change the degrees of freedom, it takes that and balances it out. Unfortunately, the new version of the degrees of freedom is atrocious. Mommy. In my notes next to this, I wrote, "Oi." Talk to me.
What does the S represent? That's in there.
Yeah, no, this S is the standard deviation. That's the calculated standard deviation for that group. So remember, that's our sample standard deviation. When I divide by the N1, that makes it the standard error, right? So notice there's really kind of a conglomeration of what's going on here. I'm using the standard error to balance the fact that I don't know enough about these two different deviations.
We're gonna have to calculate.
I sure as hell hope not. And we will find a way to do that in the software. But I didn't want you to think wait a minute, this degrees of freedom doesn't match what I used to think of, n-1, right? It doesn't even match what I thought up here, which was subtract 1 from each group. This is freaking weird. And I didn't want you to think I pulled it out of thin air. I wanted you to know somebody much smarter than me came up with this idea. By the way, this may not always be a whole number. So take this and round down. You get 19.3, round it to 19. You get 19.7, round it to 19. Always round the degrees of freedom down. Now, all of these formulas appear right here. Yes, S is sample standard deviation. Notice there's the degrees of freedom thing, Welch's adjustment to the degrees of freedom. These three boxes. Put a Post-it note here, put a flag here, put these on your formula sheet now. So immediately after I wrote my notes for this section of the book, I started doing the exercises because I said, I need to know which formula to use when. And you know what I found when I turned to page, where is it? 374 and started looking at the exercises? I saw none of them used Z. That's how rare it is. So as much as I am happy to say there are three versions of the formula, and the first one is where we know the population standard deviations, no one in this book uses it. Why did they make it first? That's dumb. I went and found an example because there wasn't one in our text. So on our Canvas page, in the in-class examples section, right there, chapter 10, section 2, 2 sample Z example. I wrote up a completely solved problem from scratch that I stole from somewhere else that uses this first version because I literally couldn't find one in our text. It's not even a business example. It's a science example. So most of the time, we'll be using the T calculation. Questions? We should do one, so it's not just me talking about this. So let's take a look at this very first problem on page 374. And it says, do a 2-sample test for equality of means, assuming equal variances. Assuming equal variances means I can do the pooled thing. Okay. We are comparing GPAs for randomly chosen juniors and seniors. The first group has an average GPA of 3.05. The second group has an average GPA of 3.25. And then they give me a lot more information. They say, oh, the first group has a standard deviation of 0.2. The second group has a standard deviation of 0.3. There were only 15 people in the first group, and there were only 15 people in the second group. Now, they said, test to see whether these means are equal or not. And that means that I want to know, does this compare with 0? And it even says a left tail test. Left tail means that my null hypothesis is to the right, and my alternate hypothesis is to the left. And they also tell me how significant. Excuse me. Okay. I need two numbers. I need the T calculated number, and I need the T critical number. I'm going to do the critical one first because that gets looked up in the table. So, T critical has alpha equal to 0.0025. In order to look something up in the table for T's, what else do I need? So what's the degrees of freedom in this case? This is the easier of the two cases. The degrees of freedom is the easy formula. Say again? It's 28. You take the two different populations, add them together, and subtract one from each. So, you know alpha, you know df. Flip to the back of the book, find me the appropriate t value in appendix for table D. It's a number you come up with off that table. However, we are doing a left tail test. I'm going to reject when I'm this side. I shouldn't use positive 2.048. I should use negative 2.048. Now, for the hard part of the actual calculation bit. This is the formula that uses the pooled variance. So I need to do the SP calculation. And I'm literally just going to copy this formula down. N1 minus 1 times S1 squared. N2 minus 1 times S2 squared. Over N1 plus N2 minus 2. Here are all the numbers I need to do that calculation. So with these four numbers right here, what is SP squared? (15 minus 1 is 14 times 0.2 squared. 15 minus 1 is 14 for the second population times 0.3 squared over 28. Somebody give me a number. That's the top of my fraction. And so I take that and I divide that by 28. I get 0.065. Now that I have that number, I can do this. What was the average for the first group? $305. Minus the average for the second group, the average for the second group, 3.25, minus what I'm wanting to know. I think we are trying to test for equal means. So my difference should be 0. Divide by. Okay, that's SP squared, 0.065 over N1 plus SP squared over N2, all square rooted. The top of the fraction is negative 0.2. .065 divided by 15 plus 0.065 divided by 15 again. Take the square root of that. 0.09309493. That's disgusting, isn't it? I'm not even going to actually try and type that number in again. I'm just going to use it right off here. I'm going to take negative 0.2 and divide by that thing. And I get what do you get for an answer? Bleh. I'm going to take it to at least 3 decimals, negative 2.148. Now we get to decide, reject or not. How do I make my decision? I compare this number with what? The critical t-value. The critical t-value is negative 2.04. Wait a minute, this is negative 2.14. We're further to the left, aren't we? We're further to the left, we should reject. Because we're doing the left tail. What does that mean? It means in this school, juniors and seniors don't have the same average GPA. There's a difference. And population 1 is smaller than population 2. It didn't tell me which one were the juniors and which ones were the seniors. I still have to figure out how to do a p-value. I'm going to do that in Excel. And we'll talk about that on Monday. I hope you all have a wonderful rest of your day. Remember, you have a homework assignment due. If you've got questions, you should be emailing me.